Hey there, so I want to talk a little bit more about derivatives this time. I'm going to review the basic ideas of what a derivative is conceptually, tangent lines, how to go about finding the derivative of a curve by the limit definitions. Now there's two limit definitions we'll talk about today. But first, let's talk about conceptually what a derivative is. So the derivative of a function, of a curve, is going to be the slope of a curve at a point. Now, when I say the slope of a curve at a point, what I mean is the slope of the tangent line of a curve. Okay. Now look at here at this graph. Notice here I have sine x graphed, and that's the blue curve here, and the red line, that is a tangent line that I have defined algebraically over here, and that purple line, the purple point here, that's the point of tangency. Now watch as I move this around, and just notice, graphically what this looks like. So notice here that the tangent line, how it's changing. Notice when I get up here to right, I can't quite get there. Oh, you know what I can do here? I can define this a little better. I could say the step is in, let's see, pi over 2. This might let me do it. Yeah, about there. Okay? Now, why pi over 2? I chose pi over 2 there because at pi over 2 sine is a 0, which that'll make sense later on as we talk more and more about derivatives. But the slope of the tangent line of sine x at pi over 2, the slope of that tangent line is 0, which makes sense that this is a horizontal tangent line right here, because a horizontal line is going to have a slope of 0. Now let's just observe what's going on here. So notice just what a tangent line looks like. Now there's different ways to think about a tangent line. You could say something like it is a line that just touches a curve at a single point. Now, of course, right there, that tangent line is not just touching the curve at a single point. It's touching down here at about negative pi over 2. And it's just touching that purple dot right there at the point of tangency. So the idea of it just touches the curve is not exactly accurate. You have to say it just touches the curve in a certain neighborhood. So if you get really, really close on both sides, let's see, that's about pi over 4. This x value is about pi over 4. So if you get really, really close to pi over 4 from the left and the right, that this curve, that red line is going to just touch the blue curve. It's not gonna cross it, just gonna barely touch it in one exact point, and that's the tangent line. But it's good to get a visualization of what tangent lines look like. So places like here, we're gonna have a horizontal tangent line. So the slope of that red line is 0 because it's horizontal. If I can get it perfectly there, I think it's about perfect right there. Right there, okay, I think if we all remember from algebra class, just kind of looking at that, that looks like that has a slope of about 1. That looks like the identity function. If you remember, the identity function is this f of x equals x, or y equals x, where it's a line that crosses through the origin that has a slope of 1. So a y-intercept of 0 and a slope of 1. Okay, so that looks like it's a slope of 1. If we move over here a little bit, looks like right there, that line has a slope of negative 1. Okay, we have a slope of 0 right there for that red line. And the values of the slope are changing as we move along here. Let's see, turn that off. Okay, so just to get an idea, remember slopes that are rising from left to, lines that are rising from left to right have a positive slope. Lines that are falling from left to right have a negative slope. Horizontal lines have a slope of 0, and then vertical lines have an undefined slope. Now I won't be able to find, in this particular function sine x, I won't be able to find a point of tangency that where there's a vertical tangent line, but in some functions you will. For instance, I could do this. Let me change this, sqrtx. Watch this. If I go over here, let me change the step over here. Let me get a little smaller. Let's say 0.1. If I get closer and closer and closer and closer, you'll see that eventually, if I could get, I'm not able to get it exactly vertical because this graph isn't fine enough here. But if I could get closer and closer to 0, this line will get very, 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 very vertical. Will get very vertical. But there's a few limitations in my graph right here. So let me go back to sine x. Okay. Now let's talk about a few more things. Let me change this back to pi over 2. All right. Now we talked about at the beginning of this chapter that one way to talk about finding the slope of this red line, or the tangent line, would to be to use secant lines to approximate it. So let me add another point here. Nope, that's not what I would do. Add another point. Let's see here. Let's add that and this. So I added that green point. Now look at I'm going to leave the red line constant. I'm going to add this orange line. So this orange line is just another line that passes through the purple line, the purple point, and this green point. Okay, a secant line is just a line that intersects 2 points on a curve. Now watch what happens. Okay, the green point is pretty far away from the purple point, but watch what happens as I get closer and closer. With the green point, I get closer and closer to the purple point. Notice how the orange line is going to get a better and better approximation of the red line. So right now, I mean, they both have a positive slope, but I wouldn't say they're very similar. But watch what happens as I get closer and closer to the with the green point to the purple point. So what would you say about the slopes of the of the orange and the red line? As I get closer and closer and closer and closer and closer to the purple point with the green point. See how the orange line and the red line are getting closer and closer, looking alike? When the purple dot, I messed up, the purple dot and the green dot coincide, then the two lines will coincide. And so that's how, messed that up. And so that's how we can approximate a tangent line, is by looking at secant lines where you have a fixed point, that's the purple point's fixed, and I have another point that I'm moving closer and closer to that purple point. Now it could be from the right, so I'm coming here from the right, coming in. Notice the orange line and the red line look nothing like right now. The orange is horizontal and the red is not. But notice as I get closer and closer with the green dot to the purple dot, that my orange line, the slope of the orange line, is getting closer and closer to the slope of the red line. And when the purple and green coincide, then the two lines, the orange and the red, coincide. You can't see the orange because it's covered up by the red line. Okay? So what you could do is you could calculate the slope of that line and then move your green dot closer. Calculate the slope of that line. Then calculate the slope of that line. Then calculate the slope of that line. And then keep getting closer and closer until you're, here I'm using h's, until h is just so small that essentially there's a negligible difference between the green point and the purple point, which then means the slopes of your orange and red line will be so close together. Now, when I say that we're gonna let this green point get closer, 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 closer to the purple point, that should bring up the idea of a limit to you. You know, the limiting process is exactly that. When you're letting an x value get closer and closer and closer and closer to another fixed x value. Let's look at what it means by the definition of the slope of a tangent line, the derivative. Let's look at that. Okay, so I'm going to move over here real fast, and let's see here. Okay, so I'm going to draw kind of a graph like we just did. Okay, let's see here. All right, so let's see. We have x and we have y. All right, let's draw a curve. It doesn't really matter, but let's change the color. Let's say here, let's have a green curve. And there we go. Okay, some curve. Doesn't matter what the actual definition of the curve is as far as x's and y's are concerned. But there's just a curve in a Cartesian coordinate system. Now, let's look at a couple points. Let's see here. Let's say there is some c value. Okay? We want to find the slope of the tangent line at c. Okay? Well, let's kind of use that idea of secant lines. Okay? Of using secant lines as approximations. Okay? Now, let's see here. If there's x equals c, then if you go straight up, hit the curve, and then go to the right, well, there is f of c. Okay? Now, let's pick another point on the curve, and let's call that c plus delta x. Remember, delta x, that's just a very small number. Okay? If I could maybe draw a good-looking delta x. Yeah, that's better. Okay? C plus delta x. So that is c plus something small, like 0.01, 0.02, or 0.001. Okay? Maybe I'm really zoomed in on the graph here, and that's, even though the distance looks kind of big, it's actually a very small number. Delta x is just a very small change. Okay? Okay, so now let's find that y value. Okay, well, that y value right there is f of my x value. So f of c plus delta x. Okay? Now, if I wanted to find the slope of this point and this point, well, I could just use algebra. Okay? Now, what are the coordinates of this point right here? X comma y. What are those two coordinates? Well, the coordinates there, we don't have numbers, but we have representations of those points. The x value is exactly c plus delta x. So let's see here. C plus delta x. And what's the y value? The y value is f of c plus delta x. Now that looks really bad, but it's not really. That's an x value and that's a y value. Now let's do the same thing for this point right here. Now let me just draw an arrow here because it's going to get kind of crowded. That point right there is, okay, what's the x value? Well, the x value is c. So the coordinates of that point are c, comma, f of c. Okay, so I have x comma y here and x comma y here. Those are just how we're defining those 2 points of the curve. Now, if I wanted to find the slope of the secant line that connects this point right here and that point right there, I could just use the slope formula. Okay. Now what's the slope formula? The slope formula from algebra class is m equals y2 minus y1 over x2 minus x1. Okay, where x1 comma y1 is a point and x2 comma y2 is a point. So let's plug into our slope formula. We could say that the slope of the line connecting these 2 points is, okay, I'm going to label my points. Let's see here. Let's get a new color. Let's say that this point right here, that is my x1 and my y1 for my slope formula purposes. And over here, this is my x2 and my y2 for my slope formula. So I could say m equals, okay, let me go back to the previous color here. We could say, okay, it's a fraction, so let's draw that. And it's going to be y2, which is f of c, oh, let me do that a little better, c plus delta x minus y1. y1 is f of c. And on the bottom we have x2 minus x1. Well, x2 is c plus delta x minus x1. x1 is c. Now there's one little simplification we can do here. Okay, we could simplify the denominator just a little bit. And we could say that the numerator still is the same, c plus delta x minus f of c over, okay, we have c plus delta x minus c, so just delta x. So this would be the slope of the line that connected these 2 points. Let me see if I can maybe draw that curve here. Now let me see if I can get this to work right. I'm trying to estimate on my tablet with a ruler what this might look like. Now this might not be perfect, it might take me a try or two, but, oh yeah, that's not right. Angle needs to change a little bit. Okay. Nope. Undo. Not quite. Getting there though. Oh, that's close enough. So that would almost be like the secant line. Well, let me try it. Well, I'm not going to try it one more time because I just took my ruler off the page. But if that purple line right there, completely crossed, right there and right there, that would be the secant line, and this would be the slope of that secant line. Now, here's the thing. I want the tangent line at this point right here at x equals c. I want the tangent line at x equals c. So what I can do is I can let delta x keep getting smaller and smaller and smaller, which will move c plus delta x to the left. As I move c plus delta x to the left, this point will get closer and closer and closer to c. At which point, when it gets infinitesimally close, I'll actually have the tangent line I'm looking for. So that's where the limit definition of a derivative comes from. Okay, I could say if I take the limit of this expression for slope, the limit as delta x gets very small, so as delta x approaches 0, that will give me the slope of this tangent line that I'm looking for. Now again, the tangent line it will be this curve right here. Let me see if I can draw a tangent line here. Again, it might take me a try or two to get this right. So not like that. About like that would be the tangent line I'm looking for. So you see there that the purple line is not exactly like the pink line because c plus delta x is over to the right. But as c plus delta x gets closer and closer and closer to c, then that purple secant line will look more and more like the pink tangent line. And the limit process is what gets us there. So let's take the limit of our expression for slope. Now, our expression for slope is right here. Let's take the limit as delta x approaches 0. So we can say the limit as delta x approaches 0 of this expression here, f of c plus delta x minus f of c over delta x. Now, do note here that c is just a particular x value. If I didn't want to solve for a particular x value, I'll do an example of this in a few minutes, then I could just have an x there, and I would get an expression. I would get a function for the derivative. Okay, this right here, when I evaluate this limit for some particular function and some particular c value, the answer is going to be a number. But if and that would be the slope at a particular x value, at a particular c value. Remember, c, that's just a specific x value. See, c is a number on the x-axis. Okay. Now, if I wanted to find an expression or a function for my derivative that I could use to find lots of slopes at different c values, then I could just let x stand in the place of c here. I'll do both ways. Okay, but here is the limit definition, or one of the limit definitions, the first definition of a derivative. Oh, you know what I could do? Since that's our definition, I could say that is f prime at c. That is, the derivative of f evaluated at c is this right here. So that is the first major definition of a derivative that we have come across right here. Very, very important. Okay, that will need to be known for tests, for homework, etc. Now, we're going to get easier ways to find derivatives, but you need to know that for sure as a base, a jumping off point to finding the other ways of evaluating derivatives. Now, there's actually another way to write this that is easier sometimes. Okay, it's called the alternative limit definition. Okay, now it's not always necessary to use this other way. Like, this will always work. There's nothing wrong with this, but sometimes the alternative definition is a little bit easier. Now, the alternative limit definition, so this is just the limit definition of a derivative. Okay? Now, the alternative definition, here let me change colors real fast so we can keep them straight. Let's go to green. Green's nice. We can do this. Start with the limit definition, and let's say let x equal c plus delta x. Okay? So if we make this substitution into our limit definition, we will get the alternative definition, which just is easier in some instances. So let's take this expression and substitute x for c plus delta x. Okay? So let's say we're still going to have a limit. So the limit. Now I'm going to have to change what we're approaching, but I'll talk about that in half a sec. Okay, originally we had f of c plus delta x. But we're going to let c plus delta x equal x. So we could say that is the limit of f of x minus, now f of c is unchanged. Now delta x, okay, what does delta x equal? Well, we know that we're letting x equal c plus delta x. So if we're letting this be true, then what does delta x have to equal? So we can say this, or we can say delta x equals x minus c. Okay? So substitute here. Delta x equals x minus c. Now, let's go back to our graph for just a moment. All we have done here is redefine this right here. We're still looking at a particular x value called c, but now we're just going to call this x right here. Okay? Now, if that is x, this x value right here, we're just going to call that x, then what's this y value? Well, it's just f of x. So that's another way just to refer to this y value right here. F of c plus delta x is the same thing as f of x. And that's true because we let x be c plus delta x. So another way to talk about this point right here, another name for it, would be, okay, that point is also x comma f of x. So x comma f of x is the same thing as c plus delta x comma f of c plus delta x. So what we're saying is, as x gets closer and closer and closer to c, the purple line is going to get closer and closer and closer to the pink line. So whereas right here we were letting delta x go to 0, so delta x was going to 0, which made c plus delta x get closer and closer to c. Well, if we're going to talk about the point x comma f of x, well, then we could say as x gets closer and closer to c, which that makes sense algebraically, because if delta x is getting closer and closer to 0, what's happening to this expression right here? As delta x goes to 0, let's say equals 0, then x is going closer and closer to c, eventually maybe equal c, maybe. So we can say x approaches c. So here is the alternative definition of a limit. So alternative definition of a limit. Oh, not of a limit, of a derivative. Okay? So we can use either of these. Now here's the difference. This right here, we're going to use if you are only concerned with one particular slope. Like the directions say find the derivative, or excuse me, find the slope of the tangent line at x equal 2. Okay? So we'll plug in c equals 2. And what we get is an answer, and the answer is going to be a number. It'll be a slope. Up here, we're going to use this definition when we want to find a function for any slope. That is, we're finding just the general derivative. We're not worried about necessarily a particular slope. We're worried about just the slope of all points in the that are possible. Now let's look at a couple examples, and I'll kind of show you what it means. So we'll need these two definitions, and let's look at an example. So let's look at. Let me turn in the book to get an example or two. Let's start off easy. Let's say just a linear function. Let me change colors here. Let's just go back to that first color. Let's say we want to find the derivative. So find, that didn't change colors. I don't want green. I want, yeah, there we are. Okay. Find the slope of the tangent line of, let's say, y equals, let's just do some nice linear function. 3x plus 2 when x equals 4. There we go. That's not hard. So we have find the slope of the tangent line of y equals 3x plus 2 when x equals 4. Okay. Or, okay, what point is this? Okay, well, when x equals 4, well, what does y equal? That's telling us at the point 4. Now, what's y equal when x equals 4? It would be 3 times 4 is 12 plus 2. So at the point 4, 14. So we're looking for the slope of the tangent line to this function at this point right here. Now, as you'll see in a few moments, as you'll see later on in the book, later on in the course perhaps, this is actually a very, very trivial problem, trivial question, but we're kind of going about by the definition right now. Now, let's use this definition here. Now, I told you earlier that we could solve this in general if we want to, and we could say, let's just rewrite this slightly. Let's say f prime at x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. What that'll do for us, that'll allow us to find the slope. Now, in this particular case, the slope is going to be a single number regardless of what definition we use, because this is a linear function and the slope is constant. So let me change that a little bit to make this a little more interesting. Let's say 3x squared plus 2. That way the answer will be a little more interesting. Okay? So here is just another way to write this, because this right here, that will give us the slope at a particular x value, although that's what we want. Like here, c would equal 4, but I'm going to solve for the general derivative, and then we can evaluate that derivative function at x equal 4 to find the answer. Okay, so let's see here. Let's use the definition. We can say that f prime, let's see here, that f prime of x equals, it's the limit as delta x approaches 0. Now let's write out what that means. It's going to be a long fraction. Now we know delta x goes on the bottom according to our definition. Delta x goes on the bottom. Now let's evaluate f at x plus delta x. F evaluated at x plus delta x is 3, and then x plus delta x squared plus 2 minus f of x. Now use parentheses here, minus f of x, which is 3x squared plus 2. If you forget to use parentheses there and don't keep track of those negative signs, you'll get a wrong answer. It's really important right there. And if you're ever in doubt, use parentheses when you're making substitutions. Okay? Now, let's do the algebra now. Now, there's the calculus. Now, let's do a bunch of algebra to get the answer. Okay? So we can say this is equal to the limit. Oh, I'm going to need more room here, so I'm going to erase that real fast. I'm going to back my equal sign up several spaces here. That's the limit as delta x approaches 0. Now let's expand this right here. It's going to still be a really big fraction. Delta x goes on the bottom. Now I'm going to have a 3. Now I need to expand this right here. Now remember, you have to FOIL that. Here's where the algebra comes in. You have x plus delta x squared. That's going to give us x squared plus 2x times delta x plus delta x squared. Here, let me fix that a little bit. Delta x squared minus 3x squared minus 2. So I distributed that negative sign. Okay? Oh, sorry guys. Let me fix this real fast. Close bracket right there. Minus 3x squared minus 2. Okay, now next line, we need to distribute this 3 right here. Equals the limit as delta x, not diamond x, delta x approaches 0. Big long fraction again. Delta x is still there on the denominator, hanging out. We have 3x squared. Now we have 3 times 2x times delta x. That's plus 6x times delta x. Let's see, plus 3 delta x squared minus 3x squared minus 2. Now, hopefully we see a few things cancel out here, and we can kind of see the answer coming to form. Let's see what we have that can cancel out. We have a 3x squared and a negative 3x squared. Those add to 0. Let's see, anything else here? We have a 6x and a delta x, 6x delta x and a 3 delta. Now, what do we notice here? Here's what's going to usually happen when we have these limit definition derivatives. What's usually going to happen is that we will work through this. Oh, I just messed that up. There we go. I meant to do this. Okay, and we will get it to where we can factor out a delta x out of the top such that we can cancel the top and bottom delta x. Now, I failed to even say why I'm doing all of this. Now, why did I even go about, at this point, not just trying to evaluate this limit by direct substitution? Because if I try to evaluate this limit by direct substitution, and I plug in a 0 for delta x, well, I have a division by 0, and that can't work. Okay? So that's why I have to analytically rearrange this, and that's why we did all those analytic limits in the previous chapter. I have to simplify all this such that I get to this next step down here, and I'm still working on the limit as delta x approaches 0. But this is kind of nice because watch what happens. I can factor a delta x. I left off something here. Notice here, guys. I did this right here in brackets. Major mistake. This happens, but you got to be able to recognize when you made a mistake. And I recognize I made a big mistake here. Watch what I did. I did the algebra wrong. I did 3 times x plus delta x squared. That's this bracket right here. And I forgot to put that plus 2 afterwards before I subtracted this off. So there should be like a plus 2. I'll just add it here on the end. Plus 2, which then we have plus 2 and minus 2. And now, this is where I was talking about on the next line, there is a delta x left in every term that's still around. There's a delta x in this term, and there's a delta x in this term. Now, I'm halfway glad I made that mistake because you're going to make mistakes. I'm not perfect, you're not perfect. But we have to recognize, be able to see when we made a mistake. Like, I started getting down to this next line, and I realized the problem's not going to work out. So I had to go back a couple lines and see, oh, where's the mistake? Well, I found the mistake right there. Okay, so practice, and the only reason I know that is because I practiced these a bunch. If you hadn't practiced these a bunch, you would get to this line and be like, well, I have no idea how to proceed because I still have a delta x on the bottom. I have delta x's on the top, but not all my terms have delta x's, and so I can't solve this. But let's see. If I factor out a delta x out of the numerator, what's left over? Well, this term will have a 6x left over, and this term right here will have a, let's see, a 3 times delta x left over. But I have a delta x on the denominator, but look here. Delta x on the top, bottom, we can divide those two terms out. So we divide those two terms out, and we are left with a limit that we can evaluate by direct substitution. So we can have the limit as delta x approaches 0. Okay, after we cancel those delta x's out, we have 6x plus 3 delta x. Now notice, we have no fractions anymore. We can evaluate this limit by direct substitution. And we can say this equals, by direct substitution, 6x plus 3 times 0, which equals 6x. Now notice, I did not directly substitute for x. I directly substituted for delta x, because we're taking the limit as delta x approaches 0, not x approaches 0. Delta x. So here is f prime of x. There is my derivative function. Now, that will allow me to plug in any x value and find the resulting slope of the tangent line. Okay? So, let's see here. I want the slope. Let's go back to the original problem. I wanted the slope when x equals 4. So I want the slope of the tangent line at this point right here. 4. Oh, you know what? I changed the rules of the problem, and I didn't change the y values. Let me erase this real fast. Let's see. What's the y value going to be? Let's change the color back to that pinkish color. The y value, okay, if x equals 4, let's see, then x squared is 16. 16 times 3 is what? 16 times 2 is 32. Times, add another 16, you get 48. 48 plus 2 is 50. So 4, 50. That is where I want the slope of the tangent line at this point right here. Okay, so let's just plug in for 4 and see what the slope is. Okay, so if f of x equals 6x, then f of 4 equals what? Well, I'll just plug in. F of 4 equals 6 times 4 equals 24. So the slope of the tangent line is 24 at that point, 4, 50. Now, I didn't ask this question earlier, but many homework questions, many test questions, many quiz questions do ask this. They ask, find the equation of the tangent line at this point right here. Okay? So, how do we do that? Well, that's just algebra class. Okay? We have a slope. We can call it m sub tan, the slope of the tangent line. And here's a point. Let's call that x1 and that y1. Well, what should come back to memory? Point slope form. Ooh. Point. Oh, let's change colors anyway. I can't even write. Let's change colors. Let's go to purple. Point slope form. Hopefully you remember this, because this will pop up a whole lot. Okay, y minus y1 equals m times x minus x1. That's just a surefire way to find the equation of the equation of a line, a linear equation. Okay, so we need a point, which we have. We have x1, y1, and we have a slope. So we can just substitute into the point slope form. We can say that y minus y1, which we says 50, equals m, which is 24, times x minus x1, which is 4. Okay? Now, that is the equation of the line, but most always we want to express that as a function of y, and put it in a slope-intercept form, y equals mx plus b type form. So let's do that real fast. We could say that y equals, let's see, 24x. I'm going to expand this right here. 24x minus, now what's 24 times 4? That's going to be, I guess, 96. And then we need to add that 50 right there. So we could say that y equals 24x. Now, what's the sum of negative 96 and 50? What's the negative 46? So here is the equation of the tangent line at 4, 50 of y equaled, okay, what was it? 3x squared plus 2. Okay? Now that, again, that's kind of like, that's the old school way to do this by the limit definition, but let's talk about a few things. Okay, let's recap. Okay? So we used the limit definition, this right here. F prime of x equals the limit as delta x approaches 0 of f evaluated at x plus delta x minus f evaluated at x divided by delta x. So we substituted in, just by the rule of what the function was, we substituted in x plus delta x for x. We did algebra. Now notice here the notation. This is very important. You hear me harp a lot about notation, and I write this on tests often that people are using poor notation. Okay, notice here I have f prime of x equals the limit here. Notice I have the limit all the way down here because I am still working on simplifying this limit quotient over here to the right. So I'm using limit notation, and when do I stop using limit notation? I don't stop using that limit notation till I actually take the limit. So here, I haven't taken the limit yet, haven't taken it yet, I'm still just simplifying, haven't taken the limit yet. I get down here, okay, I have simplified as much as I possibly can, now I can take the limit, and notice the limit is not anywhere on the next lines because I actually took the limit here. And I don't need to write the limit notation anymore. So it's really important that you use correct notation. As our course, if you're in my course, progresses, I'm at first a little lenient, but then I get more and more strict as we go along. Okay. Now we have limits throughout the class, and it's very important that you quickly learn how to use this notation. And you hear me talk about that in class, and I will always use correct notation in class, but a lot of times students don't think that's important, but it is very important to use correct notation. All right, so that's limit notation. We got down here. We had an answer here for the derivative. Notice it's a function. Notice here that means the slope of this curve is not constant. That makes sense because this is a quadratic function. Okay, that's a quadratic function, so that means the tangent lines will be changing. And at x equal 4, the slope is 24. To find the equation of the tangent line at this point here, we used point slope form, and then we just did a little bit of algebra to get this final answer here in as expressing x as a function of y, which is typically how we're going to want the final answers here. Now, let's look at this answer. Let's see if we got the right answer and see if it makes sense. So here's our original function. Here's our, nope, that's not our original function. That's the slope of our tangent line. Okay, here's our original function, so 3x squared plus 2. Let's go over here and graph it. Okay, 3x squared plus 2. Okay, so that blue curve there is the is f of x. That's our original function. Now let's get rid of some of this. Let's get rid of the, let's see here, that. We just want the red. Let's get rid of the green too. Okay, so I'm going to zoom out a little bit. Okay, so there is our blue curve. That's y equals 3x squared plus 2. And the red, that's our tangent line. Now let's move it over to the correct value, x equal 4. Let's see here. X equals 4. Now, oh, that's not good. Okay. Now, does that make sense? Does a slope of 24 make sense? Well, I think so. I think so, because that's a 24 is a pretty steep slope. And 24 is positive. That red line certainly has a positive slope. Now let's just create a new graph here, new blank graph. Okay, we had y equals 3x squared plus 2, and what was our equation of our tangent line? It was y equals 24x minus 46. Y equals, I didn't want to do that. Y equals 24x minus 46. Now let's see if that looks tangent. Yeah, I think so. That's the same one, the answer I just got. Now I picked a bad example because that's so hard to see graphically. But I think that works out. Okay. X equal 4. Let's put the point there. It was what? The point we were looking at was 4, 50. So there's the green point. That's the actual point of tangency. That's where that blue curve is going to intersect the blue line is going to intersect the red curve at exactly one point in that very small neighborhood around x equals 4. Okay. So I think I have talked about every little aspect I can about this example. The last thing I want to do is show you how you could use the alternative version of the derivative. Remember, it was the green definition there. Now here's where that would come in handy. Okay, let's say I didn't care at all about solving for the derivative in general. Because the nice thing here is that that's the derivative for any x value in the domain of f of x. Okay, so I could find the slope when x equals 0, x equal 1, x equal 2, x equal pi, x equal whatever I want. Okay, but, oh, my mouse has an idea of its own, okay? Let's say that I want to, I don't care about the slope at any x value. All I want is the slope at a very particular x value. Like here, I mean, the question only asked for the slope of the line at x equal 4. Okay, so I could have just found that one particular slope by using that green definition here. Okay, so let's show how that works. Okay. All right. Oh, I need to click back here. Oh, that's not working out here. Let's see here. All right, scroll up. Now, let's get a new thing. So we could also take the limit as x approaches c of f of x minus f of c over x minus c. That's the alternative definition of the limit. Now, we were looking at, okay, here is our c value, is the particular x value we're looking at. So here, c equal 4. Okay, and now here, remember here, there is f of x. So there is f of x. So here, if we evaluate this limit as x approaches c, that should get us 24. That one particular slope. Let's see what happens. Let's substitute in. Okay, limit as x approaches c. Oh, you know what? c here equals 4. So as x approaches 4 of f of x, okay, f of x is 3x squared plus 2, okay, minus f at c. Now, what is f at c? Well, I'll just write it out in parentheses. That is 3 times 4 squared plus 2 over x minus c, so x minus 4. Okay, let's do a little simplification. We have the limit as x approaches 4. Now we still have that x minus 4. Now, why am I even bothering simplifying this in this next step? Because if I try to evaluate this limit by direct substitution, and I plug in a 4 here, well, guess what? There's a 4 in the denominator, which we can't proceed at that point. Okay? Therefore, and actually, we'll have a 4 on the numerator as well, so it'll be indeterminate form, so we have to do some rearranging first. Okay? So let's see here. We'll have 3x squared plus 2. Now, what is this equal over here? We did this earlier. I think it's 4 squared is 16. 16 times 3 is 48 plus 2 is 50. So we say minus 50. Okay. So we can say the limit as x approaches 4. X minus 4. Okay, so we have 3x. 3x squared, let's see, minus 48. Okay. Now, we want it to analytically, we want to simplify this such that the denominator divides out. Okay, so we need to factor this. Well, how do we factor that? Let's see, we can say that the limit as x approaches 4. Oh, you know what? I should have a bunch of equal signs here. Equals, equals, equals. Okay, let's factor a 3 out. 3, then we have x squared. Now, what times 3 equals negative 48? I think it's minus 16 over x minus 4. Well, we need another line. Let's factor x squared minus 16. Limit as x approaches 4. Okay, on the numerator we still have that 3. Now, remember, this is the difference of two squares back from college algebra or pre-algebra. That factors as x minus 4 times x plus 4 over x minus 4. Now notice, we have a factor there and a factor there. Okay. Now, let's see what happens. We have the limit as x approaches 4 of 3 times x plus 4 is what's left over. Okay? Now that there's no indeterminate form to worry about because there's no fraction here, we can just directly substitute and evaluate this limit. Oh, I'm almost out of paper. So I'm going to have to go over here. So we can say that equals, let's do that. This equals, via direct substitution, 3 times 4 plus 4, which equals 3 times 8, which equals 24. So notice here, I didn't get a function for my answer. The answer was just a number, and that number is that particular slope at that particular x value of c equals 4. Okay? So, but notice it's the exact same slope I got here. This number right there, 24, and 24 down here. So we can use two different definitions to get the same answer. The benefit of the original definition, that is this one, kind of the orangish text, that benefit of that is that when you evaluate the limit definition, you get a general derivative. You get a derivative function, that is, which will allow you to find the slope at any x value in the domain of the function. So let's say the homework question asked us to find the slope at x equals 0, x equals 1, x equals 5. Well, then we could just plug in the slopes real fast, substitute, and get those, plug in those x values really fast and get those slopes really fast. But if we go down here and we used the alternative definition, we would have to use the entire alternative definition. Let's say we wanted two different slopes. Well, you would have to do this entire thing two different times. Whereas, that's a lot of work, okay? Because the answer here is a particular slope at a particular x value. Whereas up here, when you do the limit definition, you get a function of x, which then you can plug in and say, let me go off to the side here, and let's say that, slope at x equals 0. Okay? Oh, that's not a very interesting example. Oh, okay, yeah, sure, that's fine. Let's do it. Slope at x equals 0, well, plug in. Is 0 since 6 times 0 equals 0. Yeah, there's the expression for our derivative. Plug in any x value you want, and there's your resulting slope. Slope at x equals 1 is 6. Since 6 times 1 equals 6. Oh, we could keep going on. Slope at x equal 2 is 12, since 6 times 2 equals 12. See, I could find the slope at any x value I wanted to that's in the domain of my original function. And the domain of my original function right here is all real numbers. So I could find any slope I want to at any point. Okay? Whereas with the alternative definition, it's great if you only want exactly one slope at one point. And that's what it's good for. Okay? One more question I could answer, or I could pose and then answer is, what if I said, let me see here, find the points where the slope of the tangent line of f of x is equal to, it doesn't really matter. Let's say 5. Find the points. Now, I should say points, or point, like it may be a single one. Find the points when the slope of the tangent line of f of x is equal to 5. Okay? Well, the way to do that, okay, is to take the derivative function. The derivative function is f prime of x equals 6x. So set f prime of x equal to 5. So let's see here. F Solution. Set f prime at x equal to the desired slope. In our case, we can say f prime at x equal to 5. So what's f prime at x? Let's go back up. F prime at x was 6x, so set 6x equal to 5. And solve for x. Okay? So that tells us when x equals 5 over 6, that's the point where f of x has a slope of 5. And that's the only point where f of x has a slope of 5. Nowhere else. Now that makes sense because what is our function? Our function's a parabola. You know, there's, that's embarrassing. Oh, that's even worse. That's not too bad. There's a parabola. Okay? Over here, we're going to have positive slopes. Okay? They're starting off kind of small, then getting bigger and bigger. The slope's getting bigger and bigger. Over here, the slope is kind of a small negative number, but getting bigger and bigger as far as a greater and greater negative number. So starting here, the slope here is 0 at the vertex because the tangent line will be horizontal, so it's 0. Then over here, the slope is positive and getting bigger positive. Over here, it's negative and getting bigger negative. Okay, so it makes sense that there's only one spot where the slope is exactly 5. The slope of the tangent line is exactly 5. Okay, now let's verify that. Okay, so at x equal 5 over 6 is the only spot where the slope should be 5. Let's check it out. Okay, let's see if we can zoom in. We said 5 over 6. Let's see what our step is here. Step is 0.1. Okay. Let's see here. So there is the point right there. Okay. Now, let's see. The slope of that tangent line. Now I need to introduce that tangent line. Oh, this is a little more work than I thought it was going to be, because now I need the slope. Now I need to write the equation of that line. Okay, let's go back over here. Oh, now I've started. I got to finish it. What's the tangent line? The expression, not expression, the equation of this tangent line. Okay, well if the slope is 5. And the point is 5 over 6. Let's see here. So x equals 5 over 6. What's the corresponding y value? Okay, well, our function was 3x squared plus 2. So let's see. 3, now we have to square 5 over 6 and then add 2 to it. So let's see. I'm going to save myself a little trouble and use my calculator real fast. 3 times 5 divided by 6 squared plus 2. It's going to be a nasty fraction, I bet. Not too bad. 49 over 12. Okay, so y equals 49 over 12. Now, if we want to write the equation with slope equal to 5, so m equal to 5 in these 2 points, it's going to be y minus 49 over 12 equals m, which is 5 times x minus 5 over 6. So y equals 5x minus 25 over 6 plus 49 over 12. So y equals 5x. Now let's see here. 49 over 12. minus 25 over 6 equals negative 1/12. So equals negative 1 over 12. So there is the equation of my tangent line at the point x comma y when x and y are defined as such. So y equals 5x minus 1/12. So let's go back over here. 5x minus 1 divided by 12. Oh, and it looks like we did it right. Because look at there. The blue line is that tangent line just typed in. That's the point right here. Now, we want to see if that slope is 5. Now, let's see if we can count here, okay? Look at our scale. We're counting from, and these are all increments of, let's see, 4.5, 4.6, 7, 8, 9. So these are increments of 0.1 here. Okay, now the slope should be 5. Okay, let's change the scale a little bit. Let's count by ones and by ones and see if we can keep our point there. Let's see here. Okay, there's a point a little over 4, so a little over 5, going straight up. There's 1. Rise of 2, rise of 3, rise of 4, rise of 5, and then over to 1 will be a run of 1. So rise of a run, and there's a point on the graph. So this does make sense. Okay? Now, I keep saying I'm done, and then I find another question to talk about. But there are the main questions. Okay? Now, what have we done? Just to recap one more time. We used the limit definition. Or first of all, we talked about the limit definition, where the limit definition came from. Then we talked about the alternative limit definition. So original limit definition of a derivative is in yellow. Alternative definition of the derivative is in green. We used the original definition there in orange to find a limit. Now, that original definition will give you a, unless you start with a quadratic, unless you start with a linear equation, it's going to give you a slope that is a derivative that's a function, okay, that's variable. All right, so we did that. Oh, okay, and then we verified that result using the alternative definition there in the kind of the sky blue. Now, remember the alternative definition. That is when you only care about the slope, the derivative, at one particular x value. So we verified that when x equals 4, we got a slope of 24, and we verified our answer using the usual limit definition. Okay. We then graphed a little bit. Over here in pink, we found the equation of the tangent line using the point slope form. We talked about we discussed how the benefits of using the orange definition there, the original limit definition. The benefit of that is that you can get a variable expression for your slope if you start off with anything besides a linear equation for f of x. And then you can find the slope at any particular x value. That's what we did there in green. We found the slope at 0, we found the slope at 1, we found the slope at 2. Now you can't do that if you're down here in that sky blue alternative limit definition. And then lastly, what we did was we answered the question of, we found a particular x value of our original function when it had a certain slope. So I said find the points or point when the original function f of x has a tangent line with slope equal to 5. And to solve that, all you have to do is set f prime of x, which was 6x, set that equal to 5 and solve. Now, let's say that your derivative was the derivative was a quadratic function. Well, then you'd have two answers to that question. But since our derivative, right there in that light blue box, since that derivative, right here, rather, since this oh, I didn't mean to do that. Undo. Since this derivative right here is a linear expression, then when we set that linear expression equal to a number, we just get one solution. But if we had solved for the derivative and gotten a quadratic expression, we would have gotten two solutions when we set it equal to 5. Or if it was a cubic, we would have gotten 3 solutions. Okay? So those are a variety of the questions that you'll be seeing on tests, on homework. I hope this is helpful. I'll be doing some more videos, regarding derivatives, maybe about the different derivative rules and such. So keep an eye out for those. I hope it's been helpful. If you have any questions, feel free to always ask. Feel free to stop by my office, or you can always just send me an email or ask a question below on YouTube. I hope you have a nice day, and I'll talk to you soon.